Okay. Full screen. Okay, so in the last class, what we had finally looked at is how to compute the most general unifier. Um, so that was this slide, and we had gone through one example. Before I move on, do you have any questions on this example? How this example works? No questions. Okay. Um, so also, I only see 23 people here. It's, is something happening, like some interviews or something? We have 70 plus people in class, but I only see 23 people show up. Anyway, so everyone who showed up, great, thank you. I'll just follow up with everyone else who's not showed up. I've not been keeping track of assignments very closely, but 23 is a very small number. Let's see if this improves through this lecture. Anyway, okay, okay, fine. We'll continue. So, okay, so we've computed the MGU, right? The most general unifier, and that happens to be the core of the Prolog's execution. And the actual interpreter is very simple. So we are going to look at an interpreter. The interpreter is an interpreter for Prolog programs. So you load a bunch of rules, clauses, and then you have a goal. And the interpreter is going to give you either true or false, right? Or give you an actual result for the query that you ask. Okay, so, but the interpreter is going to be abstract in the sense that the interpreter does not encode explicitly the rule order or the goal order. And this non-determinism is essential for the correctness of this very small interpreter. This doesn't include any of the choice points, backtracking, or anything at all, right? But this captures the core of how Prolog works. We will see how this works, right? How the small algorithm can actually give you all the features that Prolog actually does, which is backtracking, choice points, and all of these other things. Anyway, that aside, let's look at the interpreter itself. So the input to this interpreter is a goal, right? Goal G, and then a program P. The program P is a list of clauses, okay? And the output is an instance of G. This instance is a keyword that we had defined earlier, right? An instance of a particular term is a specialization, right? So you have some substitution, you specialize it, and you get an instance of that goal. Basically, you sort of look at instances as assignments to the variables that you might have in that goal. Okay. And what will output is the instance of G that is a logical consequence of P, which essentially means that given the program P, we will find assignments for the variables in that goal or false otherwise. So this will output false otherwise. And the algorithm itself is just run with run PG. So P is the program, G is the goal. So we will use this term called resolvent. So resolvent is the current set of goals, right? So as we have seen earlier, because the body of a rule can have multiple goals, and we will have to keep track of everything. We'll just call that list of goals, the current list of goals, the resolvent. Okay. So if you initially had just one goal, say what is the length of list 1,2, list 1,2, that will be the initial goal. And as we go along, this resolvent will increase and decrease in size based on how we solve each of the goals, right? If we find a particular assignment for one sub goal and we prove it, then that goal will go away. And then if we apply a rule, then that resolvent will grow. So we'll see how that works out. So the algorithm works like this. So you initialize this resolvent to G, right? You can think of resolvent as this global variable that is always there. So given goal is now the resolvent. So we have a while loop here, and the while loop is guarded by resolvent is not empty. So initially the goal is not empty, so it goes in. So what we do first is we choose one goal, right, from the resolvent. Resolvent is a list of goals. We arbitrarily pick one goal from this resolvent, right? And say, okay, we've picked a goal, and now we have to show that this goal is satisfiable, right? Is a logical consequence of the program. So what we do is we pick some rule, right? So some clause of this form. This this form is saying, okay, you have some a prime uh, with some body. Head is a prime with some body b1, b2 to bn, right? You pick some one of the rules such that the a prime, the head of the rule, unifies with the actual goal that you picked from the resolver. So let's pick a and a prime such that they unify, and the most general unifier happens to be theta here, right? So we use the MGO algorithm that we saw in the last lecture in order to find the MGO of these two terms, right? The thing to note here is this is a general form which also includes fact, right? If it is a fact, then this B1 to Bn will be just true, right? And that covers that case as well. So that is not explicitly written out. So what we've done is we picked some rule, some clause, where the head of the clause unifies with the goal that we picked, right? That is A, and we have a MGU that is theta. Okay. So if you're not able to find anything at all, if you're not able to find such a matching clause, then we say, oh, we can't proceed further. So we exit the while loop. And if you exit the while loop, so we'll see what happens later. But if you can find such a matching clause, then what you have is you have this theta, right? You have the MGU theta. So the first thing that we do is we replace the goal A in the resolvent, the list of goals, with the body of the resolvent. So we pick all the body of the resolvent, right? We actually replace that one goal with the body, the goals from the body of the clause that we picked. That's the first thing that we do. And the second thing that we do is apply theta, apply the substitution to the resolvent, the original resolvent, right? The resolvent that we are building, and the goal G. So initially we had a G. We perform the substitutions both on the resolvent, the current set of goals, as well as the goal G. You keep doing this over and over again. And eventually what will happen is you will run out of resolvent, or you will exit out of this, right? If the resolvent is empty, then because we are specializing G at every step, the output G will be the result that you're looking for, right? Otherwise, we just output false. If the resolvent is non-empty, which means that we've actually escaped out of this while loop, right? We output false because we couldn't find any matching clause there. The one thing that we do here, which I forgot to mention, is whenever we pick a rule to unify with, we always rename the clause. So this is just so that we don't confuse the variables, right? Because we might pick the same clause twice. We want to use fresh variable names every time you pick a rule so that they don't get unified in the wrong order. So this is what we've been doing when we trace the programs by hand, right? So this is precisely what we do here. So this works out. That is the entire algorithm, right? All you do is you pick a right clause that unifies. You find the MGU, right? And then you replace the body B1 to Bn in the resolvent in for A. So you throw away A from the resolvent and replace that with the body, and then apply the theta to the resolvent in G, right? This works out. But you should be very curious now because we've sort of looked at a lot of concepts, right? We've looked at things like backtracking and choice points and so on. So how does this algorithm actually work? So so the key reason why this algorithm works is that the abstract interpreter is non-deterministic. What do I mean by that? Unlike SLD resolution or Prolog, right, which picks the rules in the order in which the program is written down and the goals from left to right, leftmost goal in the resolvent and then continue, we arbitrarily pick the rule and the goal. right? And that is the reason why it works. And here is an example, right? So consider this very simple program. So I have three facts, right? I say plus 1, 3, 4. The way to read this is 1 plus 3 is 4. And I have 2 plus 2 is 4. And I say even is 2, right? Those are all the facts that I have in the program. And my goal is going to be plus x by 4, right? And even of x, right? I say, find me the assignments for these x and y variables. Is this goal satisfiable in this program, right? If you think about Prolog, it would pick the first goal and then go on and then backtrack, right? But here, this will succeed. Let's see how. So the first observation is for plus xy comma 4, both plus 2 to 4 and plus 1, 3, 4 unify, right? Both of them unify. But if you observe the second goal, even of x, only if you pick plus 2 to 4, right? This x will be 2 here, and then even of 2 will hold, right? If you pick the first goal, the interpreter will get stuck. So if you force the interpreter to pick the goals in the order in which it is written down, then the abstract interpreter will get stuck. But the abstract interpreter is non-deterministic, right? It just says choose some goal that unifies this way. And this non-determinism is like some oracle, right? It knows which goal to pick. We have some non-determinism encoded here. And that is the reason why the way the execution proceeds is I might pick any rule at all to unify. I will pick, I mean, because this is a abstract interpreter and it has non-determinism, it can pick any goal that unifies. We will assume that it has picked plus 2 to 4, right? It picks plus 2 to 4. In which case, this goal will be satisfied, right? This goal will be satisfied, and because of the MGU will say for x it is 2 and y it is 2. And you apply this on, so there is no right-hand side. So this particular goal goes away from the resolvent. And then you take the MGU and apply to the current resolvent, which is even of x. If you apply it there, then x is 2 now. So it becomes even of 2, and even of 2 gets satisfied, right? So we don't need to encode, the abstract interpreter does not encode the actual control flow. It basically says everything is non-deterministic. As long as there is one path which can satisfy the program will succeed, right? And that's the key reason for calling this abstract interpreter, because it doesn't include precise control flow. Okay. Questions on this one? Any questions? If I change this, the thing to remember is if I change this to say, rather than saying choose a renamed clause, this one, if I say choose the first renamed clause that unifies, then this interpreter will not work, because the first clause that satisfies here will be this one, right? Plus 1, 3, 4. If you pick plus 1, 3, 4, x will be unified with 1. And the next subgoal will be even of 1, which does not hold, right? And this interpreter gets out and outputs false incorrectly. That's wrong. And the reason why it works is we leave the interpreter to choose some goal that satisfies. Okay, so that's the key bit. So this rule order is non-deterministic here in the abstract interpreter. On the other hand, right, we also don't pick the precise order in which the goals are chosen. So given the resolvent initially will be the set of the list of goals. So there will be one goal, this one, and the second goal will be this one. Let's say our abstract interpreter picks the second goal to pursue first. So it will pick the second goal, even of x, and it will look at the program, and the only possibility is even of 2, right? So it specializes this to 2, and it specializes the rest of the resolvent to with the same substitution. So this becomes plus 2 y4, right? And the only clause that satisfies with the plus 2 y4 is plus 2 to 4, right? and the abstract interpreter successfully finds the result for this program. And what the abstract interpreter will output is, it will output the same initial resolvent, the initial goal G, with all of the variables filled in, right? It will output x equals, so it will output plus 2 to 4, comma, even of 2, right? And again, the choice points are also left implicit, right? If there are multiple options, then the interpreter will output 1. And because the choice is non-deterministic, you can assume that the interpreter will have outputted all of the choices. And that's the idea of this abstract interpreter. And the key takeaway here is non-determinism is essential for the correctness of this interpreter here. Okay. So, yeah, so this abstract interpreter does not explicitly encode backtracking and choice points, right? How to recover from bad choices or present more than one result. When you give a program and a particular goal, the program is said to be deterministic if there is precisely one choice that you can make at every point, right? If there is one rule that unifies, one goal that is always there. Not every program is deterministic, and not every deterministic program is useful. But that's a point that you can keep in mind. So a deterministic program exactly has one clause for reducing each goal. So there is no multiple options. There is exactly one goal that you can pick at any point, right? And when you have a deterministic program, no backtracking or choice points are necessary, because if there is only one choice that you can pick and that choice fails, your program has failed, right? There is no recovery from bad choices because that's the only choice. And again, there are no choice points to produce more than one result, because by definition, there is only one clause that you can pick. There are no two paths. So this is an auxiliary definition that you can keep in mind. So I might ask something like, is the given program deterministic for the given goal, right? Anyway, so in your last assignment, which I think I will release today. So I'll release 2 assignments today, assignment 6 and 7. 6 will be programming with Prolog lists, and 7 will be implementing the Prolog interpreter, right? And here you will take the ideas from the abstract interpreter, but you will implement backtracking and choice points, because when you write an OCaml program cannot say non-deterministically pick one, right? It has to pick one of the choices. So in which case you have to encode backtracking and choice points support explicitly. They are naturally encoded as recursive formulations. I mean, you will know what this means when you look at the questions. But think about writing recursive programs, right? So think about, don't worry about tail recursion, just write recursive programs. If you maintain global state, the idea is that if you go down one path, right, and you perform some unification, if you come back, you need to undo all of the unifications. But instead, if you write it as a purely functional program that sort of passes the state around, you don't need to undo anything, because all you have to do is get back. And because there is no global state around, you can happily continue. All of the work for backtracking and choice points are automatically done for you. I mean, this is just a hint. You don't have to follow this, right? I'm not going to test whether you've done a recursive formulation, but it becomes much easier if you write it as a recursive program. Include no global state, right? Don't use references in this assignment. If you use references, it will become much more complicated than it is meant to be, right? And you will implement backtracking and choice points in assignment 7, right? And that carries 1/3 of the score. It will, as we've done with all of the assignments, right? It might seem daunting right now, but we will slowly build it up. So we'll slowly give you small pieces that you need to finish up, and we'll have test cases. Once you have that, this naturally builds up to the entire thing. So don't worry about building it from scratch. You'll be provided all the skeletons. You just need to work out the core algorithm. So yeah, so that's what I wanted to say about the abstract interpreter for Prolog. So okay, so that sort of finishes one part of our Prolog exploration. So what we've done is we looked at some Prolog, but we also looked at a lot of ideas about backtracking, choice points, and so on. So in the rest of the few lectures that are left, what we'll do is we'll look at one concept, but but it will be more of applications of Prolog, right? So we'll use Prolog to encode interesting things, and that is what we'll focus on mainly in the rest of the lectures. So let me move on to the next lecture, which is mutable data structures. I have a question mark because that is a hint for saying that Prolog doesn't have mutability, right? It doesn't have support for references or anything. But we can encode things that look like mutable data structures in a very clever way, just by using unifications, right? And we'll see that in this class. Yeah. So last class we looked at Prolog. This class we'll look at simulating mutable data structures in Prolog. So far, right, in our exploration of Prolog so far, we've used variables. We've used variables in many places. We've used variables in particular only in queries or clauses. So when we query, we might use a variable, or when we write down the Prolog program, we use variables. But we have not used variables in actual objects. We've not used variables within functions, right? Functions as in functions according to what Prolog defines as functions, um, but not in compound terms essentially. So let's see an example. So here is a list. Okay, so where I say L is unified with this list, where where it has 1 and 2, and the tail is going to be x, right? And what I get back is L is 1 to x. So in Prolog terms, we call this an open list, right? And the idea is that it has to be 1 comma 2. Let me change this now. So this is called an open list because this is some list which has 1 comma 2 as a prefix, right? And the suffix is not defined. So we actually leave the suffix to be a variable. So it could be anything at all. So this is useful, right? We can pretend to extend the list L by unifying X with something else. So by unifying X with some other list, we can pretend to make the list have more structure. In particular, let's take this example, right? So my L is going to be 1 comma 2 bar X, and then I say X is 3 comma 3 bar Y, right? Now these two variables get unified. So L now happens to be 123y, right? The prefix is 123, and the suffix is y. X is 3y. So of course we are not doing mutations here, right? This is not what is happening here. But if you sort of just focus on this, right? L happened to have 1 comma 2. If you ignore the tail for the moment, L happened to have 1 comma 2. Now L happens to have 1 2 3. Of course the suffix is different. We'll come back to that. So this, we are going to just play around with this idea of looking just at the prefix of lists, right? And we are going to pretend as if the initial list has 1 comma 2, and now the list has 1 2 3. And what we've done by unification is extend the list. We've added one element to the list, right? And this sort of reading is known as open list. Of course, this reading is sort of just giving you a hint. It is not a precise definition of what the list is, but that's the idea that we are going to use in this lecture. Okay. Any questions on this so far? Okay, no questions. Okay, so let me continue. So, so one thing that the Jupyter interface to Prolog does badly is deal with open lists. So if let me do this one thing. So I'll restart the kernel. And observe that the query that I have is L equals 1 comma 2 x, right? I should have L to be 1 comma 2 with the tail x, right? But if you run it in the Jupyter notebook, what you have is an incorrect list, right? It says L is the list, the closed list 1 comma 2. L precisely has 1 comma 2 and x is some variable. This is not correct, right? This is incorrect. This is just a failure with the Jupyter notebook interface. The result should have been L equals 1 comma 2 x, right? Again, this is not correct. So for this lecture, what we will do is we will not write code examples in the Jupyter notebooks because it is not correctly representing open lists. We will directly do everything with the Prolog interpreter. Okay. So what we'll do is if you say, let me open a terminal. Let me make it bigger. So if I do L equals 1 comma 2 x, oops, I need a dot. So now the Prolog interpreter correctly tells me that L is 1 comma 2 x, right? So this is what I expect, but the Jupyter notebook does not give me the right answer. So I'm going to not focus on the Jupyter notebook for the code examples in this particular lecture. Okay, so let's continue with that. Okay, so what we will do is we will use open lists to represent queues. Okay, so we are going to deal with queues mainly in this lecture. So what is a queue? Queue has first and last out, right? If you put in something, it comes out of the front last. Yeah. So a queue, we will represent a queue with this compound term with the top function symbol q, right, which has arity 2. And we'll have two parameters here, right, both of which are lists, right? L will be an open list. Okay, so L is an open list. And E is some suffix of L, right? E will always be some suffix of L. So the way we will read this queue is, this is just a notational thing, right? The way we will read this queue is the contents of the queue are all the elements in L that are not in E, right? So, so here is an example. So if I write down Q is 1, 2, 3, and 3. So the way to read the Q is that the Q contains elements 1, 2, right? The definition is that you take the initial list and you remove the suffix that is represented by the second argument. The suffix that we have here is 3. So we will remove the suffix. So 3 goes away. So the Q's content is 1, 2. So we will read this as Q has element 1, 2, right? And this is the notation that we will use for the rest of the lecture. So these are, this is how we will encode Qs. This is a very particular form of representation. It's sort of, it is not intuitive at first, but it sort of lets us explore this idea of open lists further. So when I write a Q 1, 2, 3, 3, observe that the prefix, the original Q, the first element has 1, 2, the first component has 1, 2, 3. The second component is the suffix that is removed from the first component. So 3 goes away. So the list contains 1, 2. Questions on this one? How we do this? This is just a notation that we will stick for the rest of the lecture. Okay, no questions. Okay, let me continue further. So what operations do we have for Q, right? We have push and pop. So we will use the predicates enter and leave for representing push and pop. So the idea is that enter and leave captures the idea of elements entering into the queue and leaving the queue, right? And both enter and leave have arity 3. And the way to read enter AQR is that when an element A enters the queue Q, we get the QR, right? So a way to read, the other way to read this is if you push A into Q, you get R out, right? And leave says that when an element A leaves Q, you get R. So this is also can be read as if you pop Q, you get A, and the resultant Q is going to be R, right? So that's the enter and leave. So here is the definition of. So we have two more things here. Um, so we have this idea called setup and wrap up, right? So the idea is that setup is meant to initialize a queue. So that's an empty queue, right? So an empty queue is represented by some variable A, some variable X, and then the suffix is also the same variable. So going back to our definition, right? We say the content of the queue is the content of the first component minus removing the suffix, right? And because the suffix is the same as the first component, this queue does not have any elements. So that's the way you will read it. So we initially set up the queue. So this is sort of initializing the empty queue, right? And then wrap up is meant to hold only on queues which have both empties, right? So this is meant to sort of unify with the term where the queue is completely empty. Empty in the sense both of these queues are empty. The initial queue here is also empty. This is also empty. The idea here is rather than using a variable, we are actually using an empty list, right? So I think that's the only difference here. But this is useful to say we've sort of consumed everything from the queue, right? So that's the idea here. So we have setup and wrap up. So we will use the setup and wrap up later. But here is the definition of leave, right? So what does leave say? Leave is like a pop operation, right? So you're going to take an element of a queue, and the resultant queue is going to be the third component, right? So when the variable A leaves this queue, which is q x comma z, you get q y comma z, right? And A has left the original queue, right? Which means we are going to take an element from the first queue. So, and the way we represent that is x is one element A added to y, right? So x has ay, and if you remove A, you get y out, right? And that's what we are representing here. So the queue has an element. The front element that we have is A, right? And if A leaves this queue, then what you end up with is q y comma z, where y is basically A const with x is basically A const with y, right? Questions on this one? I might have not explained it in the most natural way, but any questions on this one? All we are doing is we are popping an element, right? When you pop an element out, we say that we name that element A goes away, and we are left with yz, right? And x happens to be A const y. Okay, maybe this is obvious. But the next one is a little bit strange, right? So enter, right? Enter is push into the queue. And the difficulty here is this is an open list usually, right? So we cannot, because it's an open list, the suffix is not defined. We cannot push to the end of the queue. So we have to play this little trick. And the trick that we play is, so assume that this y happens to have an element A in the front and the tail is Z. So recall that the second component of this queue data structure is meant for the elements that are being removed from the queue, right? So Y is the set of all elements that is not present in, that is going to be removed from X, and that will be the elements that are present in Q. So what we are actually doing is we are removing an element from Y, right? And that becomes Z. So we are removing an element from the second component, the suffix, so that an element actually enters, right? So this is um, um, so we are taking off an element from the suffix, which will be the list of elements that will not be present in X. If you take an element out of this Y, you will have one element into X, right? And that is what we represent here. So in order for A to enter into this Qx comma Y has to be AZ, right? And you drop A from the second component, and that becomes Z. By dropping an element from this is at the subtraction side, right? By dropping one element, you happen to magically have one more element here. And that's the idea here. It's a bit strange. So if you look at the examples, it will work out. So let me actually run this example, and it will become a little bit clear. So here is the all the Q definitions, right? And then what I'm going to do is I'm going to copy this setup and then enter. So when oops, let me exit again and do it again. So user Control D, and then if I first do setup Q, right? So if I do setup Q, observe that all setup does is it says that there are some variables XX, right? And this just happens to be Q is just unified with that. So Q happens to be some variable underscore 9172, some variable underscore 9172. So that's fine. We've set up a Q. If you do setup, that is all you get, right? Everything is satisfied. If you now actually take this empty Q setup and then push 0, if 0 enters the Q, then you get R, right? Let's see what that does. So now you see that Q is actually unified differently now, right? Q is an initial list, right? Which is empty. So the way it is empty is quite strange, right? We say that the first component has a 0 and some suffix, and the second component is the same component, right? Because these are the same, this Q is empty, right? And all enter does is it drops the 0 from the second component, right? That is what enter does. And if you drop the second component, what happens is you get this R, where the first component has a 0 followed by 9592, right? And the second component is just 9592. So the actual content of the Q is 0, right? By dropping a value from the second component, we actually make an element appear in the first component, right? So this Q has one element. This Q has 0 elements, even though 0 is there, right? Because of unification, we happen to have zeros here. And this Q has just one element. It's a singleton Q with value 0, right? This is a little bit different from what you will have seen earlier. So I'm sure you have questions. If you have questions, interrupt me, right? And there are no dumb questions. I think this is like what people say all the time. Any question is a good question, right? If you have questions, do interrupt me, and we'll proceed, and then we'll see. But do interrupt me even if I'm talking, right? Just post the questions, and then we'll get back to it. So what is happening here is we are removing 0 from the second component, right? And that makes this queue actually have one element. So that's the way we simulate adding an element in the queue. So in turn, the way to read this is that leave removes an element from the prefix, right? Leave x has an element a, and that element is removed. So leave removes an element from the prefix, and enter is the dual, right? But it happens to remove an element from the suffix. So y happens to be az, and enter happens to remove an element from the suffix because the suffix is the set of all elements that will be removed. If you remove an element from the suffix, the element gets added. So it's like it's a very funny thing that happens here, right? But it's the exact dual of what enter does. Sorry, leave does, and we're just choosing the position to remove an element, right? Okay, so let me proceed. Let me actually proceed. So here is an example. What I'll do is I will do this example one step at a time. So let's work with some queue, right? So when you set up a queue, all you say is this queue gets unified with this setup. So we have the variable xx here. So this initial queue is empty, right? And let's say we are pushing one element a into the queue, right? If you push, I have the initial queue q, and I say a enters q to give me the qr. So observe that the initial queue now is unified with this term which has a in the front, but the suffix also has a. So this queue still has no elements. This queue still has no elements, but R has one element, right? There is an A. The suffix is there, but this is the suffix that will be removed. So R has one element. Let's push one more element into the queue, right? So if you do this, what we are saying is um, push B into R. If B enters R, you will get S. So observe that the initial definition also has changed, but Q still has 0 elements because these two terms are the same. R has one element A, right? So this A is there, but the suffix is the same as the one here. So R has one element A. S has two elements, right? A comma B, because this suffix is the one that is here. That will be removed. And then what you have what we are going to do is pop one element from the queue. So Q has A comma B. The thing that you will pop will be A, right? So I say, let me pop an element X from S. S is the last Q that we were working with. If you pop an element from S, let's call that element X, you will get T. So we expect that X to be A. So let's see whether that is the case. X is A, right? And you're left with a Q which has just a B, right? And this T happens to have just B because the suffix is the same. This suffix is the same. And if you pop one more element, you'll get B, right? And we say, I'm going to name that element as Y. So we see that X is A and Y is B. The second element that we pop is B. And what you end up with, we push two elements, we pop two elements. So we end up with the QU, right? Where these two components are the same. So U has no elements at all. U has no elements at all. And we can wrap up this, right? We say this Q has no elements. Let me just wrap it up. And if you wrap it up, all wrap up does is it unifies this variable with empty list. And that unification sort of replaces all the 998 with empty list, right? And you get this. So initial Q happens to be empty. When you push an element, you get A. When you push B, you get B. When you pop, you get A initially, and the Q is B. When you pop again, you get B, and the last Q is empty. Right? That is what we have here. So here's a short quiz, right? Um, so we have Q, uh, the Q's Q, R, S, T, U, right? What are the lengths of Q, R, S, T, U? You can type the answer in the chat window. Yep, right. So 0, 1, 2, 1 and 0. Okay, good. Um, yeah, I should have more quizzes. I'll do that for the next following lectures. I think this mode is sort of very bad for not having any feedback. I'll see some nodding heads if you are in the class, or like staring faces, which will give me some feedback. But anyway, so the answer is 0, 1, 2, 1, 0. So the strange thing with this implementation is because these enter and leave are duals, right? Unlike regular queues where you need to push before you pop, here you can pop from an empty queue with the contract that you will push the same element, right? So here is a very strange use of queues, but this is perfectly fine in Prolog, right? We say we start with the empty queue. I pop an element out. I name that element to be X. I pop one more element out. I name that element to be Y, right? And then I enter A and enter B, right? Then I push A and B, and then I wrap up. So let's see what happens when we do these three. Oops, just these three first. Um, yeah, what I'm saying is this queue will be empty, right? And then I pop an element. I pop one more element here. Let's see what happens. So it says that the initial queue is empty because these two are the same. And then this says, oh, uh, I've lost X here, right? This is sort of very strange. The suffix actually has one more element than, sorry, the second component has one more element, X, than the first component. What this says is there is some X which needs to be filled in later. And similarly, if I leave again, if I pop again, all I say is I will add a contract for later, which says that oh, the suffix has two more elements than what the first component has. So if you fill in these two components, right, I will consume those. So it's like a negative queue that way. So if you now enter A here, right? So now it says it unifies that with um, A here, right? So what happens is it happened to be the case that this had two negative elements, right? And because we've entered, this is going to fill in the first element. So X is going to be A, and you can do the same thing for B, right? Just to complete the argument, there is still minus one element here, right? There is some Y which is not there in the prefix. So if you enter again, that element is going to be filled, right? And that Y happens to be B now. So I pushed B, so Y happens to be B. So Y happens to be B here. And the queue has become empty, right? So U is empty, so I can wrap up the queue. So this is quite a strange way of looking at queues, but in a purely declarative fashion, this works, right? So we are not actually manipulating things in an operational way. We are actually doing it completely declaratively. What this means is you can take elements from an empty queue with the contract that you will add elements later, right? So if you wrap up, that is what you get, right? When you wrap up, you get initially it is yeah. Anyway, you know what is happening here. So here is a question again, right? This is the same example. The code is the same as previously, right? And what are the lengths of Q, R, S, T, U now? Yeah. So that's the answer. I already got it right. Um, so initially it was 0. and this one has -1 element, right? R has -1 element. This has -2 elements, and this happens to have -1, and this is 0. So really, push and pop are not very different. If you think about, I mean, this is really curious, right? At a high level. So if you sort of even imagine functional version of queues, take lists, right? I can always cons onto a list, right? But I can't always get the tail of a list because the list could be empty. So there is something that is not exactly mirror image. The push and pop is not mirror image, right? You can always push into any queue at all. You will just get one more element, but you can't pop an element from any queue because you can't pop an element from an empty queue. So this even though push and pop are duals of each other, they sort of break down at this empty queue, right? Um, but that is gone here. So the thing that happens here is you can pop from a empty queue. You just happen to have a contract which you have to satisfy later. So it's a really curious way of thinking about push and pop that are completely duals here. That's the high level takeaway here, right? Um, Let me format it better. Okay, so I hope you've got the point of this, right? So even though this looks like push and pop, they are really push and pop in the declarative sense. They are really mirror images of each other. Unlike, say, push and pop that we have on, say, imperative or functional languages. Yeah, 0, -1, -2, -1, 0. So last quiz, I'll stop here. So what is the result of this query? So I set up, I leave an element, I pop an element, and then I wrap up. Yeah, so the answer is false because wrap up will only work with, just to show you what happens. So wrap up only unifies with empty list, right? And what happens in this example is Q has 0 elements, right? R has -1 elements. You can't wrap up a queue with length -1. You get wrap up queues with length 0. And that is what happens here. Anyway, so, okay. Oh, there happens to be one more. Maybe I'll stop here. So we've looked at queues, right? So queues is first in, last out. What is the enter for last in, first out stack? Yeah. So 2 is the answer, right? So we are not. So stack is much less interesting because we are not playing this negative game. So all we are saying is we are not going to push element at the end. We are going to push at the front. So so if you enter A into this stack, which has X as the prefix, then you get Y, where Y happens to be A const X. So this is much less interesting, right? But otherwise, if you just change enter, then all of this will work. And also this, you can play these negative games with the stack as well. You can keep leaving and then keep pushing. So that will happily work out. Yeah, that's the answer. So I'll stop here and then we'll continue tomorrow. Thank you.